So the ionic strength is going to affect the effective concentration of our ions in solution. How do we quantify that? How do we keep track of that in terms of mathematically? So what we'd use is what's known as an activity coefficient. And this is a coefficient that keeps track of how non-ideal our ion is behaving. And these activity coefficients are affected by ionic strength, but also by the ion itself. How big is that ion? What's the charge on the ion? That will also affect the activity coefficient. So if we have, say, some chemical species C, not carbon, but just some chemical, we write the activity. Let me spell it right. We give it a fancy A, capital A here, and subscript it with whatever it is. So in this case, it's our ion C. And that will be equal to gamma for ion C times the concentration of C. And again, this is generally in molarity in most cases. There are exceptions. We could do this in other units. Okay, so this gamma here, this is what we call the activity coefficient. And this multiplies by our concentration to adjust it for the non-ideal behavior. So if gamma is equal to 1, then we have ideal behavior. And that's sort of the assumption that we make for many of our equilibrium calculations, is that we say, okay, we are going to assume ideal behavior and we're not going to worry about activity coefficients and ionic strength. And that's generally what you did all throughout general chemistry. And for many sorts of problems where we don't need terribly precise answers, this is good enough. But when we do need precise answers, we do need to take activity coefficients into account when we're thinking about equilibrium. And then in general, for ions in dilute solutions, gamma C will be less than 1, generally speaking. So and particularly as the ionic strength increases, this activity coefficient will tend to decrease, and then it'll reach a low point and come back up. But that doesn't particularly matter. So the proper way to write an equilibrium constant is not with concentrations, but it should actually be K should be all activities, and that gives us the actual value of the equilibrium constant, because that takes into account the non-ideal behavior of the ions in our solutions. So our equilibrium constant should look like, if we have, A plus B going to C plus D, should look something like this. Right, the activities of each of our species raised to the appropriate stoichiometric coefficient. And so we can write this out as our typical equilibrium constant that we've seen before with our concentrations. And then we'll end up with an extra term with all the activity coefficients. So gamma C to the C, gamma D to the D, gamma A to the A, gamma B to the B. And again, these will be raised to the activity coefficients.